Hello, everybody. Welcome here to this tutorial from me and my colleagues from JKU. Yeah, you can guess from the title, this is a tutorial on symbolic music. So if you're here, you may want to know more about this kind of this kind of data type, musical data type, or maybe you already know it, but you know also that it's very complicated to handle. And then you may just want some like help in that, some examples. And we are going to do that with this new Python package that we are presenting that is called Partitura. And you're having many things today in this tutorial. You're having an introduction on symbolic music by me, just to explain what this kind of data can contain, because it's not, it's much more complex than it may seem. So we need some general information about that. And this will be a theoretical presentation. And after that, we have hands-on sessions with code examples, with data sets, with models that will be trained on this kind of data. So let's start from symbolic music. And before starting, a small disclaimer, because the packages nowadays is focused on Western music notation. This is a big limitation that is unfortunately in common with most of MIR research. Unfortunately, our expertise is limited to this kind of music. But if anyone with expertise in other kind of music is willing to talk with us, we will be more than happy. Okay, let's go inside. So symbolically encoded music that we call for short symbolic music is a kind of musical data type that represents explicitly some information among note pitches, note sunset and duration, voices, and other stuff like key signature, time signature, stuff like that. So I say explicitly, this data must be encoded, must be present. For example, audio is not a symbolic data type, and at the same time, a raster image of a music score is not a symbolic. Is not symbolic music. Instead, we have two common data types that are musical score and performance, and I'm going to introduce them. As I said, there must be some explicit representation of note duration, and the musical score actually has all of them. So it contains information about note pitches that you can see here. That will be the vertical position in the musical score, if someone of you is not very familiar with this notation. You have note durations that tells how long each note lasts. And first important detail, this will be specified in musical unit in the musical score. Musical units, there are many, but you can think about beat, for example. You can think about quarter length. So this first note, for example, is 3/4 of a quarter length. And in a 4/4 measure is 3/4 of a beat as well. This is not related to seconds in any way. It's just a musical unit. That's how we call it. Then we have onsets. Then in the musical score are just the cumulative sum of the previous events, of the previous durations. And as I said, this is not related to physical time. But if you have this symbol here, that is tempo indication, then you can switch from musical units to physical time. Also, the duration and onsets are what we call quantized. So there is a limited set of symbols that is used in the score. So that means a limited set of durations. That means a limited, the position of the onsets are quantized, means that some notes just play together, some don't play together. And they are aligned to some sort of grid that is not, that is coarse. Other information in the musical score are voices that you can see here highlighted, and other things like key signature that is giving some information about the tonal context, and metrical positions. Metrical position, you have time signature here that you see 4/4 in this example, but also the bar line that you find in a score. It gives you some metrical position with some, and some position will be stronger than others. And this can be represented, for example, with a tree, as has been done in many research. So I just give you a very small introduction on the musical score. There are many more informations. For example, you see this tempo indication. There are dynamics indication like this piano and forte, like other stuff like ritardando, and some symbols that tell you that a note should be very long. And I mean, that's very, very rich kind of encoding. And that's also why it's actually so complex to use. So how is this produced? Because yeah, if we can model all this as much as we want, but if we don't have real examples, I mean, we cannot do anything with that. So usually, musical scores is produced with a notation software, music notation software. Here you see an example. This is MuseScore. That is a free one, but there are many others like Finale, Sibelius, Dorico. And so usually someone sit down and type notes in these notation softwares. So then you can specify exactly like the pitch, the duration, and all the other elements that I showcased before. There are other ways, of course, like through automatic transcription, through OMR, but that's the main way these scores are created. Okay, so this was the musical score as one kind of symbolic music data type. Let's move to the second. The second is what we call musical performance. So if the musical score is created by someone typing notes on the computer, the musical performance is created usually by someone playing an instrument. So a musical performance can be represented like this. So this is just a representation that is called piano roll. You will see that more in detail in the later sessions. But that is very useful to visualize what kind of information are contained in the musical performance. Because you have like note pitches, again, like as before, this is still symbolic. So this is encoded in the y-axis in this two-dimensional matrix that you see here. You have, again, onsets and duration, except that now these are not quantized. This is unquantized because these are produced by a real humans playing an instrument, and the humans are not perfect. That means that even if they want to play like 3 notes at the same time, there will be a very small variation. You can see here, for example, all these notes are supposed to be played together, but because of the deviation introduced by the player, then they are kind of misaligned. Another very useful information is the velocity. The velocity tells us how fast the key is pressed. And this is usually related to the intensity of the sound that is produced. Okay, so this was the musical performance. Second, very important data type. Let's talk 1 second about encoding. That's also the most annoying part because that's what we will need to deal with when we do MIR in this kind of symbolic data type. So for the musical score, of course, the musical score and the performance are very different kind of data, then they are encoded in a different way. So the musical score is encoded with some files, like you see here, some examples. There are many standards like MusicXML, MEI, and Kern are probably the 3 most used nowadays. What about performance? Performance is usually encoded in what is called MIDI files. And this is a binary file, so we cannot even, I mean, we can open it and read. If you can read binary, I cannot. So usually we go through some sort of representation, like some sort of parser. This is really necessary here. Okay, so let's resume because this needs to be very clear because there is usually some confusion in the community about what is score, what is performance, and how to treat them. So I just recap. Here you can see the main differences. So musical score, we have musical unit, not seconds, okay, like quarter notes, for example, beats. We have some hierarchical time representation with bar measures and with the time signature. We have the pitch spelling. Yeah, I haven't talked about that before, but this is some information that is in the score. So if you are familiar with this notation, you know that you can have this F sharp, for example, and the G flat will also encode exactly the same frequency, except that it contains some different information about the tonal context of the music. So this information is there in the score. And then you have a lot of many other information like key, time signature, voices, temporal indication, dynamic indication. On the musical performance instead, you have time expressed in seconds, or some sort of things that can be translated to seconds. The representation is just sequential. You just have a sequence of not onset, not offset with velocity and pitch. You don't have pitch spelling, like the same frequency is encoded in the same way. And but you have a very precise timing and velocity of each note, like you know exactly when this was played by the musician. The musical score is encoded in MusicXML, MIDI kern mainly, and the performance in MIDI. So what about MIDI scores? So if some of you is familiar with this, you know that I mean, some people use MIDI files as scores. Indeed, the MIDI format is able to encode many information that are part of the musical scores. So, for example, the MIDI format is able to encode musical time units instead of seconds. It's able to encode some time representation, like with bar measures, not pitch spelling, but also key time signature and stuff like that. So this is some sort of simplified musical score. It will not look anymore like that. It will look more like that. So this is, you see that all the notes here are aligned because the score is quantized, as I said before. And there is also some bar line that you can see on this image. And yeah, so we can say in some way that MIDI can be used. However, we cannot say that MIDI can encode a score. Like a score is much more. Is also a graphical object that people can read. That's not true for MIDI. People cannot read a MIDI file. If you give a MIDI file to a musician to play, it will not be able to do that. So this is something that is just more low level. However, it's very useful because it's a bit simpler to parse. There are some data sets that are just using this format. So it's useful to know, but it's also important to keep in mind that a MIDI score is not as rich as a full score, let's say. And it's also very important to keep in mind that a musical score, even encoded in MIDI, is not a music performance. They encode very different kind of information inside. And this is the source of many errors, like also in the community, some people write, we produce a musical score, but maybe they produce just a performance, or maybe they think they've reached, like, they've achieved like full transcription, while this is, I mean, there are still some steps to be done to build a full musical scores. And that's not trivial. Okay, here you see just an example of this. Here you have a full musical score. Down you have a MIDI score. You see that all the events are aligned, like the stuff that are chords in the musical score are on the same onset, exactly on the same temporal position. And on the right you have a MIDI performance of this that was played by a human. Okay, so this division, so I presented to you a division in score and performance. This is not something that we invented. It's something that was theorized by Babbitt, that is an American composer and music theorist, a mathematician. So he proposed this modelization of music, where there is a part that is the performance, that is the produced musical experience. There is a written part, that is the score, that is what's written by the composer, and there is an auditory part. So we are not really interested in the auditory part in this tutorial. However, we will use the performance and the score a lot. Okay, so I give you some introduction on the data types. You will see then more in the hands-on tutorial how to use them, and then you can also explore a bit more than the differences that are inside. Sorry. Okay, there is a third data type that we will use in our presentation that we call music alignments. So this is simply a set of links between a performance and a score. That's all. Just for each note of the performance, if you can identify a note in the score, you will link it. So that's what we have. This is very important, for example, if you want to compare different performance of the same pieces of the same piece. You want to know where each note is correspond to the score, or if you want to do like music transcription or some task of MIR, you need this kind of alignments. Okay, so then for the people in this room, some people may be already expert in using audio. So like the question is why using symbolic music? Like indeed audio is easier to produce because you can just play an instrument and record it. data set of audio files are usually bigger.
Sorry,
yeah.
1 second. People
no problem.
Thinking about the bad video quality. So
okay.
I just want to do one change. Can you log into Zoom? So the same link.
Which one?
Sorry,
Yeah, for the online participants, we are going to solve some technical issues. So a couple of minutes. Thank you. Okay, we are back. Okay, sorry, they told me that the video quality was not so great. However, the slides will be also available then. We will share the link so you can find all the material. And you can probably follow from there. Okay, so we are at this point, we explained like the kind of symbolic data type that are available, plus this one that is not so used, but we use it a lot internally, and we hope you will as well. Yeah, so why using symbolic music? So that's the big question now, because audio is more available, it's easier to produce, the data set are bigger. And okay, however, like there are some advantages. So some kind of research, some kind of question are better targeted by symbolic music. So there are some advantages. The first is that there is a less noisy representation of musical content, because the content of a MIDI file or a score don't depend on a microphone, for example. So all these things, all these confounding factors that you have inside of recording, you don't have them anymore. You don't have anymore in a symbolic file. It can give you better interpretation if you're striving for that in your application. Also, you can point to a specific group of encoded events. Like if you want to know which note is causing something in your system, you can do that with symbolic. With audio, it's harder because you cannot. Audio is like vertically mixed. That means that all the notes that are on some audio position we are not really able to distinguish them. I mean, we can do some work about that, but it's not so easy to point, for example, in a spectrogram. It's not as easy as pointing to a note in a symbolic format. And then also, even if you're doing research from audio, it's still very useful to know how to deal with these files, because you can have a lot of ground truth information inside musical score, for example, or you can use them for data augmentation, like to synthesize a new data set, a synthetic one, and stuff like that. Also, like more people in the community are using MIDI files over scores, and that's very understandable, because musical scores have been very hard historically to deal with. There are some packages like the one we're proposing and others that I will show you later that helps a bit, but that's usually a bit complex to extract some sort of meaningful information. So people usually just try to skip it. However, the musical score contains higher level musical information like this metrical hierarchy, and maybe most importantly is readable by humans. So if you're doing some generation task and you want people to be able to read the pieces that you generate, for example, to play them, then you need to pass through musical scores. Like generating MIDI files is enough if you want to play them automatically on your computer, but not to have people play them. Okay, so now that I introduced symbolic music, so let's talk about MIR, because that's the focus of the conference. So usually you will have, I guess this is a common pipeline for many of you. So you will have some data files. In this case, they are symbolic files. You want to extract some feature from them, and then you feed this feature into some machine learning model that is predicting or generating something. So we are presenting Partitura today. That is a Python package that deals with the first part of this pipeline. So we want to help people to just take a data set, download a data set of symbolic music, can be musical scores or performances or of alignment, and just as fast as possible produce a feature that you can then feed in your machine learning model. That's very useful, because some people may not want to deal with all the exceptions that are present usually in symbolic data formats, or some people may not have very high musical expertise, but only, for example, deep learning expertise. Then we want these people to be able to target also symbolic problems. And that's the focus of our library. So if you're familiar with symbolic music, you may know that there are other libraries that have been used to do this, to extract feature. The most famous one are Pretty MIDI and Music21. So there are also other libraries that are coming out more recently but whose focus is more maybe on generation or like specific kind of tokenization, stuff like that. So instead here, they are the one like generic one that have been used just to extract some generic features. And we don't want to replace any of them. That's not our goal. It's not to have a ultimate package that you can use instead of the others. Instead, we want to position our package in sort of a middle ground, because Pretty MIDI, so it's very, very easy to use. It's focused on extraction from MIDI files. However, there are some limitations, like there is no real distinction between performance and scores that, as I showed you before, that are very different data types. So you may want to treat them differently. And Music21 is a package for computational musicology. Is very complete, has many options inside also to create scores and a very advanced nested representation of music. However, it's a bit hard to use, and it's not very optimized for a lot of to just produce feature. Like you need to do some work starting from the score. So it's very good if you want to like look specifically into one score and find what is going on, or creating some score or modify them. But instead we want to focus more on the feature extraction part. During this tutorial, we will use 2 data sets that you can then also use in your research. They are publicly available. So the first is Vienna for time 22. That was kind of a standard data set for the alignment between score and performances. It contains just 4 scores and 22 performances of each score. That's why it's called like that. So 88 performances. and it had around 43,000 notes. However, this is a bit limited because for score, usually, I mean, if you're running some sort of task, you really risk to overfit on these 4 scores. There is not enough data. So we also like propose to you today this extended version of the ASAP dataset that contains 222 scores and 1,062 performances. And this is the biggest dataset with this fully alignment. So because each note is aligned to from the performance to the score with around 7 million note alignments. This is a work that is still under review, but the data are available to you and we will use them today. Okay, I will finish my part with some presentation of the team. So we are 4 people here that you see. You will meet them later. There are other people from the JQ University working on that. And there is, of course, the guy that started all the project. That will be the benevolent dictator for life for this package. Okay, so this was the introductory part. If you have questions, I can take them on this part now. Otherwise, you may want to open this link. Here you will find all the material for the, sorry, you will find all the material for the next session, like, yeah. So let's, yeah, if you have any question. Otherwise, I will take like 3 minutes just for us to switch a bit. You can open the link and yeah, see you in 3 minutes.
Okay, good morning, everyone. Very nice to be here in this cinema-like tutorial room. I hope you can hear me on all channels where you're supposed to hear me. I'm now kind of lost of which chats I should keep track of. I don't know if there are any questions on Zoom or via Pigeonhole or via Slack, and I missed them. Please just shout. Yeah. Please just shout in the room or try to make yourself noticed. This is also not working. Okay, I opened the link that Francesco just showed in the very end of his presentation. I also posted it to the Slack channel. If you go there, you will see a web page generated from the tutorial notebooks that we're going to use today. I hope you all have access to this. If you click on the first one on the left, you will see this static generated web page, and I'm going to open it in Colab and work in Colab. If you prefer to run these Jupyter notebooks locally, it should also be possible. Just grab them from GitHub and run the environment setup, and you should be good to go. Otherwise, just open it in Colab, log in, and we can start in there. I assume pretty much everyone is familiar with Colabs or notebooks. They are made of code cells and text cells. The text cells explain what is going on, and the code cells execute Python code. You can execute cells by either typing on, clicking on this little arrow button on the left. Is this large enough on my screen? And here we have the first code cell. We can click on this arrow, or we can do mark the cell and do Shift Enter. For the first cell, it will ask you whether you trust us. Please do, and then we can continue. Are we ready in the room, at least? Do you need 2 more minutes? Do you have it in front of you? Show of hands, who is ready? Okay, I give it 2 more minutes so you can set it up. I think this tutorial makes most sense if you really have it in front of you and can continue along with us and test your own ideas right away or what Partitura has to offer. Is a link missing? Okay, the Q&A during tutorials is Pigeonholes only, and you will keep me informed about it. Okay, how are we doing now? Are we ready? Who's ready with the notebook, Colab, whatever it may be in front of you? Does anyone still need time? No, looks good. Okay, let's get started. First technical stuff of this year's ISMIR, so I hope you're cozy and relaxed. The first notebook has 4 sections. The first 2 are self-explanatory. The first one is install and import. The second one is about I/O functionality of Partitura. Then we're going to have an in-depth look into the internal representations, in particular of musical scores in Partitura. And we're going to have in the 4th section look at how to retrieve useful machine learning features from these objects. I'm going to go very quickly over these very first cells, since they essentially just set up your Colab locally. we will install Partitura from pip, and we will import some other libraries that we use in here, mainly NumPy and a few visualization and sonification utilities. And we're also going to download the aforementioned Vienna 4x22 corpus, which contains 3 different modalities of symbolic music that you memorize now, all of you. We're going to mention it over and over again. Once we have the scores in the MusicXML format, we have performance MIDI files, 22 for each score excerpt in this dataset. And lastly, these 2 modalities are note aligned. So for each note in the MIDI performances, we know exactly what note in the score they correspond to for this dataset. Now we are already at section 2, loading and exporting files. Like, I assume this is probably why most people might want to use Partitura, is that it gives you a nice utility that loads plenty of different score or symbolic music formats and just gives you machine learning ready representations out of the box. So this might be important information on what you can actually load with it. Let's start with symbolic scores. Symbolic scores like sheet music source. We were able to load MusicXML, MIDI with the caveats mentioned by Francesco that it's not a complete score format, MEI, Humdrum Kern, and MuseScore if you have a local MuseScore executable installed. For symbolic performances, we can load MIDI. I'm not aware of any other symbolic performance format actually, so I guess this is complete. For alignments, we can read match files, which Carlos is going to talk about in depth for the next in the next section on alignment, and 2 different formats which are produced by note alignment algorithm by Nakamura et al. For export, it's a bit more limited, but we still support MusicXML export as well as MIDI, of course. And for performances, same. We can export MIDI and match alignments. All right. Now for the big chunks, internal representations. I'm going to start with score representations of sheet music. It's much more in-depth, much more complicated than the performance stuff, which will be at the very end of this section. So I'm going to have plenty of little bits on score representation. And in the end, we're going to get to MIDI. And for the next section, it's going to be the same. It's going to be like pretty much focused on one thing, and only the performance is a little bit on the side. When you load musical score, be it MEI, be it MusicXML, be it in Kern, you load it via Partitura, you get a score object. Score object is not a particularly important object for you. It's just a wrapper. It gives you some meta information about the composer and the piece, and it is furthermore an iterator over the part objects in this score. The part object 3.1, this is the core Partitura representation of musical material in scores. This is like the thing that I'm going to talk about for the next 20 minutes or so. This is the name is, if you know MusicXML, it's kind of inspired by MusicXML. MusicXML speaks of parts when it speaks of single instruments usually. Parts might have multiple staves, such as grand staves. There are sometimes part groups which correspond to like sections in an orchestra or instruments that are grouped together. In general, in one part, we have a single instrument and 1 or 2 staves representing the musical material that is played by this instrument. Each part object that is loaded by Partitura is a timeline object. It follows a timeline ontology. The whole, all the musical material is sorted along a time axis. So we have one arrow of time inside each part object, where the time is measured in integer diffs. When you load a score from outside, these diffs are chosen such that even like the smallest time unit necessary in the score can be represented in integer units. All score objects, and this is a very abstract and vague term, but all score objects are timed objects, meaning we place them on this timeline ontology at a certain starting and ending point. As I said, all external files, score files, are loaded into such part objects, and these part objects can also be exported into score formats. All the utilities that we're going to talk about relating to extracting information features from these parts are methods that attach to the part object. Here we have a visual representation of what this looks like, what I just talked about. We have this part timeline. We have several time points on this timeline, and for each score object, we model each score object, such as nodes or time signatures or clefs or rests, as timed objects, which means they have both a starting point and an ending point, which get tied to specific positions on this timeline measured in integer diffs. For nodes, this might be very trivial, right? We're very familiar with nodes having a certain onset time and a certain duration. For others, it might be kind of weird, because what really is the time of a clef, and we take the position of the clef or of a time signature to be the position at which it is visually encoded in the score, and it is then active until we encounter a new timed object or score object of this type. So the time signature is encoded at a specific point on this timeline, but is basically active until we reach a new time signature. Okay, enough of the abstraction. Let's get some code. In this very first cell, we have 3 lines, which is all you need to get started with your first part. We point to an example MusicXML, which is built into Partitura, and we load it using load MusicXML, and then we index the return at 0. This is the score object caveat that I just talked about before. The load MusicXML returns a score object. For this, we're only interested in the part object, so we just retrieve the first part in this score by setting this index to 0. Next, we print a prettified tree of this score, of this part, and we see that we have a timeline with 3 different time points, and for each time point, we have several different starting and ending objects. By the way, just below this, we can have a visual representation of the corresponding tiny little part that we're modeling. So we see we have 2 states. We have time signature of 4/4, we have a rest and 3 notes, and 2 clefs, twice the same clef. What does it look like as a tree? We see that first thing I already omitted when talking about what I've seen visually. I didn't mention a measure. There was also a measure in there. So on the tree, we can see there is a measure. We have a starting node. We have also a page. We have a rest starting at 0. We have a system starting at 0, and we have a time signature. What else is to note here? We have the time points. T equals 0, and next to it we have a mention of quarter equals 12. The time points are in these integer diffs. The next number, the quarter, tells you how many diffs correspond to 1 quarter in the current part. It is not the time in quarter notes, right? Yes. A changing diff.
can do the deep parting.
Yeah. This is possible. All right, probably the most familiar musical material are notes. Let's retrieve a list of notes from this part. This is done as easily as typing part.notes, which gives us an iterator, or in this case a list, over notes as encoded by Partitura. Let's see what the note properties are by uncommenting the next line. We see that this timed object, even though it is very simple and basic, already has a lot of depth. So we have in these notes stored a lot of information related to this specific note, such as visual things like a beam, whether musical things such whether there are articulations, and also encoding information such as the document order in the original MusicXML file. We can, of course, create new notes using Partitura. We do this by using the class partitura.score.note. We give it an ID and pitch in step and octave information. We also give it a voice in this case. Note that the note itself doesn't yet have a position on the part, which is create like a free floating note, and it will only have an onset time and the duration once we add it to the score. I also uncomment this next line such that we can see how the score changes, at least in this tree representation. So we have these two new time points, t equal 3 and t equal 15, which now have each just one starting object and one ending object, which is exactly the notes that we generated before. If we want to remove a note from a part, we need to have a handle of the exact object that we want to remove. And we can then call part.remove with this handle and remove it. Print again the tree representation, and you see that these two time points are no longer represented in this timeline because there are no other objects. I talked about diffs a lot already, and I mentioned why they are useful. They are, however, not super useful for human usage or for musical for downstream tasks that make use of musical units. So we usually convert them into something that means a bit more to us, such as beats that are related to time signature or quarter units. For this, Partitura makes use of so-called maps. We have several different maps that map between different time units, such as beats and diffs split, beats and quarters, and diffs and vice versa. Here, this you retrieve the beat map corresponding to a specific part by typing part.beatmap and then give it a time point in diffs. In this case, I give it the ending time of the first note in the part, and I get an NumPy array, which is just a single value, which is 4. Let's have a look at this, whether this is actually true or whether we made a mistake. I think the first note is the one that starts at the very beginning. Well, actually, it doesn't really matter which note we pick. They all end at the very same point. They end at beat 4, which is the end of the first measure. Besides mapping between different time units, such as diffs and quarters, we also have maps related to high-level score information that is active at a specific point in the score. such as time signatures or key signatures. If you want to retrieve the time signature or the key signature at a specific point, you can use the corresponding maps. If you want to retrieve the currently active measure or the encompassing measure of a specific time point in a part, you can use the measure map. Or if you want to retrieve just the measure number, you can use the measure number map. There is information regarding the metrical position, and of course the time mappings that I talked about. Now, in many cases, we want to retrieve some specific score objects from a part, such as retrieve all measures or retrieve all notes of a certain type. In Partitura, we do this by using the part.iter_all function. This is our main utility to retrieve score objects. It takes 5 inputs. First one is, and all of them are optional. The first one is a class, a class of timed objects that you want to retrieve, such as notes or measures. The second one is a flag, whether to include subclasses. This is especially useful for different node types. We have a generic node from which all specific node types inherit, and specific node types mean things like grace nodes or unpitched nodes or the standard node or even rests. Sometimes you don't want to iterate over all objects along the whole part, but you want to give it a window from where to search. So we have a start time and an end time in this iterol. And there's also a mode parameter, which lets you retrieve objects that start within this window or that end within this window. And the default is starting. First example is iterating over measures. You do this by creating this iterator and passing as the sole input the score object measure. Second is a little bit more involved. We want to iterate over all generic nodes, including subclasses, and we give a specific window. So here we retrieve 2 objects, actually. Again, here starting and ending time are given in diffs. You remember from before, the quarter duration was 12. So if we start at 0 and end at 24, we actually have a window of 2 beats or 2 quarters. And we retrieve all the information in this first window, which is in one voice just the rest, and in the other voice this whole node in the second staff. If you don't want to pore over the internals of Partitura and figure out what the names of all these classes are, there are a number of list properties already available in the score, in the part object. We noted this in this second subsection. We mainly have notes, tied notes, measures, rests, repeats, key signatures, time signatures, dynamics annotations, and articulation annotations directly retrievable as lists from the part object. So you do not need to generate your own iterator. Okay, this is the first time we have a little bit more code, and I'm going to skip it right away. This example, 3.6, puts together everything that we've just talked about with regards to retrieving and adding stuff to parts, and does this by way of an example, which lets you generate a new note at the end of the last measure, at the currently last measure, independent of the type of musical material that you have underneath. So you do not need to know anything about the part. This code will just work. It serves as an example if you want to go from there. I, however, want to go straight to the next somewhat random example, which we called cats on keyboard. In this example, we're going to generate random scores. we're going to generate them somewhat similarly to how you would generate a random MIDI file. And we just pick a pitch, pick an onset time, pick an offset time, and encode these notes. However, I want to underline that this goes a little bit beyond just generating a random MIDI file, because we're actually able to produce a well-structured musical score from this type of random information that we use here. So we can afterwards export it to MusicXML and use it in whatever kind of task that needs to have sheet music representations and additional information regarding musical material. First, we have a helper function, which is called add note, which just takes a part and puts a note on it, encoded in this particular way that we use here. We then set the length of how many notes per voice we want to have. We have 4 voices in this example, and we want to have 100 notes. Generate a new part, give it a name, give it a quarter duration, which is set for this part. Then we generate a number of durations and a number of onsets per voice, and stack a number of pitches per voice. We then loop over all this random information that we just generated and add it to the part. Lastly, and this is at the heart what I just said before, how is this different from just generating a random MIDI? We do add extra information, and namely, we do add time signature, we add 2 clefs, we have two staves in here. And we also do these last 2 steps, namely adding measures and tying notes. Now, what does this mean? The first one is clear. We didn't add any measures before. It was just like a series of notes, just as you would have in MIDI encoding. Here we use the time point of the first note plus the information available with respect to time signature to place measures on this part, as many as are needed. And in the last step, we kind of sanitize the note information with regards to the underlying score, meaning that if we now have notes crossing measure boundaries, we want to represent them as tied notes instead of just ugly notes that cross these boundaries. We can store them to MusicXML or to a score MIDI. If you work in Colab, this will show up in your Colab here on the side. You click on this folder button and you will see all the data. You can download it and have a look at it with any score viewer you might have installed. Do you have any questions so far? Online, nothing either. The grace?
Yeah, the grace. How is the grace note presented in the partitura?
A grace note is represented as a special class called grace note. They are pretty much identical to other notes, with the only exception that they have no duration.
So
they just have like
the same start and end.
They have the same starting and ending point. In some cases, they have just set none as an ending point.
A none as an end point.
Yeah.
Okay, thank you.
We have for some cases where you need, for instance, we will see this later on, for piano rolls or for some downstream tasks, we want to expand grace notes such that they have a duration such that they are actually visible in our features. And for this, there is functionality to expand grace notes. But on the part, they're represented with just a single time point.
what about trills and glissando?
What about trills and glissandos? How are they represented?
Trills and glissandos would be represented as a specific type of ornaments. So this is like in addition to the notes, like extra meta information for the note. At least for trills, which are and glissandos, which are written on top of a note or a specific position. Other ornaments such as acciaccature would be fully notated as grace notes. But yeah, it depends on the type of ornament, how it is encoded in particular. Okay, in the meantime, I think MuseScore managed to open this beauty of a score. If you follow along, you can do it as well. It just goes to show that there's a little bit more to like a fully specified score than just random musical information, and Partitura manages to create it if you're ever in need of a completely arbitrary score. We can also represent it as a piano roll, and we're going to talk a little bit more about this in a second. And also, Carlos is going to talk a lot about piano rolls in his part on in his session on alignment, and we can also listen to it. I'm not going to play it right now. Would be nice if everyone in the room played it at the same time. No, but if you have headphones, use them and have a listen to a nice sine tone rendering of this completely randomized score. Okay, that's it with the first part on scores and their main object, the parts. I'm going to continue very quickly with the performance object and the performed part object, which are the partitura representations of MIDI performances. Again, as before, as for the score object, the performance object is probably not very important to you. It's kind of a wrapper object and also an iterator for the contained performed part objects, which correspond to unique MIDI tracks. One performed part is much simpler than a part. It just contains three main properties. One is the notes property, which gives you a list of MIDI notes encoded in, as dictionaries, a controls property, and a program changes property, which gives you the corresponding MIDI commands. And we have some utility with respect to to generate note arrays from these and adapt offset times according to pedal information. Let's do the same thing as before. We point to a MIDI file, an example MIDI file, and we load it using load performance MIDI. By the way, I think Francesco gave a nice explanation to why we talk about score MIDIs and performance MIDIs. This is obviously inspired by the type of material that we used and researched in the development of Partitura, but load performance MIDI will load any kind of MIDI file you might have. It doesn't need to be like played solo piano recorded on a Bösendorfer Grand or something. You can load drums, you can load whatever MIDI file you might want to have. It just means that it doesn't do these additional steps of trying to derive score information from the MIDI file. Yes, please.
Is it possible to encode tablature fingering information?
No, we haven't worked. Sorry.
Yeah, thank you. Is it possible to encode tablature information fingerings from?
Yeah, very nice idea. No, it is not right now. This would be an extra step to think of what format of tablature would be most useful and how we want to represent them. I mean, the generic note or the part framework is fairly open with respect to symbolic encoding formats that we might want to read, but we do not have a parser or probably really any idea of how we would go about this or what the common formats are.
Thank you. Thank you.
Thank you. More questions in the room or online? Nope. Pedal information. I can also just repeat the question if I understand it right away. That one.
What about pedal information? Can we add that to the measures?
Yes. Pedal information is stored in MIDI files as control change.
Right.
So if it is pedal information from a piano is stored as control change, and this would be stored in the performed part.controls list.
All right. Yeah.
So you get a list of dictionaries corresponding to the CC value and, well, the value of how much you want to have this control change value activated.
All right. And this also translates to the sheet.
This corresponds to?
And this also translates to the sheet. So when we have a score, does this pedaling information also
No,
there?
the pedal information is not used in the generation of a score.
I see. Okay. Yeah.
There is, maybe I can talk about this for a second. Here we have the performed part notes list. In this case, also again an example MIDI. And so we have 3 notes in there, and each note is basically a dictionary of information. Here we have some influence of the pedal. I'm just gonna, if you're familiar with MIDI, you will be familiar with most of these keywords. They are MIDI pitch, a note on in seconds, a note on in MIDI ticks, a note off in seconds, and a note off in MIDI ticks. Track information, channel information, velocity information, an ID, which is not part of MIDI, but we uniquely assign an ID to all MIDI files, which is important for stuff that Carlos is going to talk about later on. And we also have this sound of property, and sound of property is related to pedal information. For things that are piano music, we can use the current position of the pedal to retrieve the time point at which a note would stop sounding. If the pedal is fully pressed, even though the note might be very short, the MIDI note might be very short because the actual key press is very short, the note still keeps on sounding, and it will keep on sounding in this framework until you release the pedal. But this is not true in reality because it will stop sounding eventually, but in this case, we compute the sound of time like so. For scores, we have no way of encoding pedal information.
So we have a parser for
A parser for the pedal?
So if the score contains so pedal information like the ped and then a start at the end, so this is encoded and this would be loaded.
Yeah, if we have pedal annotations in a score, we can load this, yeah.
Mm-hmm.
But not like performed pedal as MIDI.
And you can
Sorry,
create
maybe
them.
I misunderstood you then.
You just, it's a, okay. All right. Okay. So how is the pedal off information is represented? So is it like velocity becomes 0 for the pedal when the pedal is off?
I have to make sure to not make the same mistake of not knowing what you talk about as before. In the case of MIDI performances, where we have actual pedal information stored in CC values, you can set the threshold at which you want the pedal to stop working. This is how it would work in most DAWs. It's not entirely realistic for how pedals work in grand pianos, but you can just set the threshold, for instance, to 64, which means at some middle value, it would stop.
Yeah, I mean, like the channels are from 64 to 67 for the pedals, and then if a pedal is on, then the velocity probably it's set to something, and then if the pedal is off, the velocity goes 0. That means we know that the pedal has been released. Is it
exactly like you get?
So did you use Pretty MIDI for parsing the
Whether I use Pretty MIDI?
Pretty MIDI for
No, we
person?
don't use Pretty MIDI underneath.
Okay.
We get it via Mido.
Okay, Mido.
Yeah.
All right.
Yeah, exactly. It's pretty much this. We get the MIDI C values related to the pedal position. And if the pedal position is such that the pedal is fully depressed, we would say it is active. And if it's above a certain threshold, we would say it's not active at the moment. For the score, it would be, again, it would be a timed object annotation of pedaling information. They would have a certain starting point and an ending point. Okay. Now I'm going to close this again so I get some more screen real estate. The fourth section of this first session on introduction to Partitura is called extracting information from scores and performances. We assume that most of you would want to use Partitura not in this in-depth way that we just talked about, by figuring out what individual timed objects are called and what their classes are and where they inherit from and so on. But you want to retrieve this information from a score and get it into your machine learning pipelines as easy and uncomplicated as possible. For this, I'm going to show you a couple of ideas how to get this information out of the score part object without having to deal with it directly, and how to represent it. I'm going to mainly talk about note arrays and different ways of generating note arrays, which is lists of notes where each note is one row. Then I'm going to quickly talk about piano rolls. Carlos is going to talk about it a bit more. And in the very last bit, I'm going to talk about how to use our implementations of some standard automatic music analysis algorithms to retrieve, or in most cases, estimate like higher level information relating to scores. Okay, let's start with the note arrays. Note arrays, in our case, are 2D arrays. Each row represents a single note in the score or performance, and each column is a different attribute of that note. Note arrays are not wrapped in any kind of Python object of our making anymore. They're output as pure structured NumPy arrays, which are just ND arrays where each column could have a different data type and has a field name. We can retrieve note arrays from parts and from part objects, and we can also add extra information to these note arrays by first setting a number of flags in the corresponding function, by giving note feature functions, and we can also create custom note arrays by computing our own. And we're going to go over these different use cases right now. As before, we point to a MusicXML file. In this case, we're going to load one of the scores that we downloaded in the beginning in the Vienna 4x22 dataset. We're going to load it using load MusicXML, and we're going to generate a note array by calling score.noteArray, open parentheses, close parentheses. Now, this is the first time that we did anything on a score object and not on the part object. It would work exactly the same on the part object in the case that you have several parts in a score, orchestral score or whatnot. You would just retrieve all the note arrays of all the parts and put them in one big note array. Let's have a look at what's in there. Would it be possible to close the door, maybe? Doesn't change the thing. Okay, thank you. We have the first 10 notes represented as these rows of score information in the note array. We see underneath an excerpt of this score with the corresponding notes marked with their IDs, what they refer to. This will already give us some information, what the fields or what the individual columns might represent, but we can also just retrieve the field names and print them. So the fields that we're going to work with in this standard type note array are called onset beat, duration beat, onset quarter, duration quarter, onset diff, duration diff, pitch, voice, ID, and diffs per quarter. By now, I assume this is all already self-evident for you what it's supposed to mean. Onset beat is the onset time in beats. Duration beat is the duration time in beats. The onset time 0 is in Partitura the first time of the first measure. In case we have an anacrusis measure, we might have negative numbers in there, such as in this case. We actually have an incomplete first measure and anacrusis measure, so the first 6 notes should have negative onset times. The next 2 fields are related to timing information in quarters, and then we have it in diffs. For quarters, we have the same thing, that we have the time point 0 at the first measure. For diffs, 0 just means the very first element in the score. So diffs are always positive. The last information should be clear as well. It's pitch. Again, it's represented as MIDI pitch, but the note information actually contains more. With voice information, we have ID. We can do the same thing from a MIDI file by, again, pointing to a performance MIDI in this case from the Vienna 4x22 dataset. We load it using load performance MIDI and create an array by typing performance.note_array. Here, our D types are somewhat different. Of course, it's a different representation. We, out of the box, get onsets and durations in seconds and MIDI ticks, as well as pitch, velocity, which doesn't exist for the score part, track information, channel information, and the ID I talked about. Let's have a look at 5 notes of these. So as you can see here we have a good example of how it is important that the data types of these different columns can be different. For the first 2 fields, the time is encoded in seconds, so we use floating point values. And for the second 2, we use these MIDI ticks, so again, integer values. For those who have it open right now, we have prepared a little sketch where you can generate performed a note array. You can perform a note array by typing on your keyboard and copy it here, generate a perform part object from it, and export it to MIDI. So just to show how this note array for perform part is very well embedded in the structure of perform part. So if you click on the link, you will your browser will open this window of this little sketch. If you click on the gray area and type Q, you will see that a playhead starts moving. And if you then type notes, play notes on your keyboard, it will generate a piano roll from this. After 10 seconds have passed, it will output the corresponding note array information down here. So you can copy all this, bring it back to your Colab and copy it in here. So as the perform part doesn't really, at its core, it doesn't really contain much more information than what we can also pack into a node array. So it's easy to create perform parts from node arrays as well. And we might want to export our little creation to a MIDI file and use it somewhere. Now, if we're interested in more information than what we've seen so far in the basic node array, we can go about it in 3 different ways. And I'm going to talk about one after the other now. The first one is using the flags of the node array function. We have built-in additional information related to including pitch spelling, key signature, time signature, metrical position, and grace note, where grace note basically means this node is a grace note and what grace type it is. Let's set them all to true and check the field names of the resulting node array. As you can see, this is already much more than before. For instance, we included pitch spelling, so it's no longer just a MIDI pitch, but we have information related to the step, alteration, and octave, which is the triplet that we use to encode the pitch spelling information. We have this field is grace, which encodes whether something is a grace note, and so on. As this is a structured NumPy array, we can retrieve a number of columns that we want to use in a specific task by just giving a list of column names, of column field names. In this case, ID, step, alter, octave, KS fifths, KS mode, and is downbeat, and get a smaller but custom node array. Again, this refers to the first 10 nodes in the excerpt we've seen above. But now we have per node also information related to the key signature. Here we point, oh, what did I do? Can I not click on this? Okay, so the key signature information is related to the circle of fifth. You can see in this column, it says -1. So we have 1 to the key signatures, including flat accidentals. And next to it, it says 1, which means major in this case. So we know that we are in F major for all of the nodes. Surprisingly, we are in the same key signature for 10 full nodes. 2 of those nodes are downbeats. They have an encoded 1 in the is downbeat column. This corresponds exactly to these 2 nodes that are at a measure boundary. If this was still not enough, we have in music analysis a number of node feature extractors implemented, and which you can pass to a different kind of node array function, which is called partitura.compute_node_array. We're going to see this in a second. And you can pass to this function a part as well as a list of node feature functions, and it will give you a very complete information regarding these nodes related to all the features that we can extract from them. If you want to get a list of what information is implemented, you type partitura.musicanalysis.list node feature functions, and you get the following list of node feature functions, and you pick the ones you're interested in. Here we are interested in metrical feature and metrical strength feature, again with the part as before, and we want to see the first 10 nodes. And now we have, in addition to the core node array information such as onset and duration in different timing formats, we also get like information related to metrical strength. If you don't find what you need in the node features and in the flags and in the basic node array, we have some example code as to how to add your own custom features to these node arrays and use them for whatever task is at hand. I'm not going to go over this in detail. This is there for your reference. In this case, it will encode accentuation, whether this note is accented in the underlying piece. Two more small sections on what information can be retrieved from the part and perform part objects, or score and performance objects, to make them usable. First of them is piano rolls. Now, piano rolls, for some of you, the thing that we call note array might already be a piano roll, but when we talk about piano rolls with respect to Partitura, how we see them, we see them as 2D matrices that represent pitch and time information. In most cases, we have time information in the horizontal and pitch information in the vertical axis. You give time information at a specific time division, and it encodes in this matrix where a note is active at this specific time point. It's kind of like the symbolic equivalent of a spectrogram. How do we use them in Partitura? We use, as before, we point to a location, we load it into a score object, and we use partitura.utils.compute piano roll and pass it score, a part, a perform part, you name it, whatever is your wrapper of your musical material. This will compute a SciPy sparse matrix, since most of the time these piano rolls are pretty much zero everywhere, because note information is very sparse. If you want to turn it into a standard NumPy matrix, you just type 2 array or 2 dense. Of course, you can specify a number of things about piano rolls as well, such as the time units or the range of notes that you want to have in there. Again, Carlos is probably going to show more functionality related to piano rolls. Let's plot one of these. Actually, I already gave it away since we plotted one when we generated the cats on keyboard scores, right? But this is what you would expect for a score piano roll. Here we have encoded as ones whether a note is active at a specific time point in the horizontal and what piano key it corresponds to in the vertical. This is no longer MIDI note, but this is piano key in this case, since this is how we generated this piano roll. For performances, we would also encode, in the most cases, we would also encode velocity in the value and not just whether the note is active or not. If you do not only want to have the piano roll, but also get the note indices that correspond to a specific note in the piano roll, you can set this return indices flag to true, and this will return you a second object, which looks like so. It is a list of lists where each quadruplet corresponds to a note. The first thing is an index in the vertical related to the piano roll at hand that we generated. The second and third are onset and offset point of this note. And the last one is the MIDI pitch. In this case, MIDI pitch corresponds exactly to the index in the piano roll, but this does not necessarily need to be the case. We can also go backwards. We can take a piano roll, information and create a note array from this. And as we've seen before, we can create a perform part from a note array. So in case you're working with piano rolls and you generate loads of them using, I don't know, some CNN VAE, and you want to know what kind of musical information is actually available in your output, you might use these built-in utilities to generate note arrays and perform parts. And in the following MIDI files from your initially generated piano rolls. The last thing I want to mention is built-in music analysis, automatic music analysis tools. These do not generally just retrieve information. These are usually just standard algorithms from the literature that do estimate information. We use them mainly if you want to have like a full score information from MIDI, but you can also use them as baseline results for comparison. If you have some new pitch spelling algorithm or some new key estimation algorithm, you want to just compare it to a baseline implementation that is already out there. For this, we have the following informations in the following algorithms in Partitura.musicanalysis. We have algorithms related to voice estimation, key estimation, pitch spelling, tonal tension, and meter, beat, and tempo estimation. All right, this is it for the first introduction to Partitura. Do you have any questions?
Thank you. How are the directions like in tempo markings or dynamic markings like a crescendo pianos are like in passed in the partitura?
They are. It depends on the marking. Like some very exotic ones are just parsed into timed objects called words, but dynamics markings such as crescendi are marked as dynamics markings. So there is a specific object for these, and they're also placed at the specific point on the part and retrievable via part iter_all and partitura_score.dynamics markings.
Okay, thank you.
And we can have a look at the documentation for all specific types of things that we retrieve from score information. Do we actually have this? I mean, there's a nice example for this here, because we made a mistake and wrote andante here instead of andante, but it's correctly parsed as a tempo direction andante, which doesn't really make sense, but it's parsed as a tempo direction object. And the text, as it will be in the score, will also be in the direction. So if you have mistakes in the score, they will be represented in the part as well. Anything else? No? Good. Thank you very much. I think we're going to take a longer break now, right? Like 20 minutes or so, and then continue with alignment and 2 different ways of using Partitura in machine learning workflows. Thank you. At 11, we're going to 11:05. We're going to continue at 11:05.
because they're doing a lot of work. Got it. Oh. Sorry. Sorry. Okay, yeah. And so then we have some theoretical frameworks of how to conceptualize music and how to analyze things. These are always theory-driven, and they will then change the way that we interpret music and which elements are we considering for music. One of the most important probably is the GTTM, so the General Theory of Tonal Music, which is a formal grammar-like type model by Jackendorf and Lerdahl that quite a few people in MIR has tried to implement as a computational model. There are also some theoretical approaches, information theoretical approaches like the idiom model and the multiple viewpoint system. And there are, of course, computational approaches to more traditional Western music analysis like Schenkerian analysis. We have also like the traditional tasks in MIR, so in music analysis and musicology, like analysis of structure and harmony and pitch and meter and whatnot. We will at least have one of these tasks for the last part of the tutorial. We have performance modeling from a symbolic perspective, since we can record a lot of performances with MIDI capable instruments, and we can do analysis and rendering of performances, which is an active area of research. And probably one of the most common domains for symbolic music research is music generation. So be it as fully automatic composition or as part of interactive systems or something that just generates parts of the composition like harmonization or accompaniment. And finally, we have these inter and intra-domain applications where we are using symbolic representations as the end or as the beginning, and we are communicating with other domains like music alignment that aligns things between representations, either just symbolic and audio or any other representation. We have music transcription, which starts with audio, and then we get a MIDI-like representation or a symbolic representation. We have optical music recognition, which starts with the images directly, digitized images of the music, and then we generate a symbolic representation. And of course, synthesis, so how we transform the symbolic elements into something that sounds the way that we want. And with this, we move to the second part of the tutorial. So if you are on the web page, we move to the part of symbolic alignment. So I hope you all are there. But yeah, so we start with symbolic music alignment. This is kind of one of the fundamental technologies in MIR, because it links representations of the music across multiple domains. And so it refers to the linking of musical signals of the same musical work, be it different versions of a song or different performances of the same piece, or matching a performance with its score. And alignment is generally done in 3 steps, which we represent here in this figure, which is inspired by Meinhard Müller's book. Starts with some representations of the music. In here, I refer to like the actual MIDI files or live input. And from these representations of the music, we extract some features, which is our general MIR pipeline. So be things like a piano roll or encodings with neural network or whatnot. And then we have finally the alignment methods themselves, which take the representations and generate the alignments. So we are going to explore this in more detail. So let's start by setting up the notebook. And while this is setting up, I will talk a little bit about these three parts, right? Music representations, features, and the alignment. For music representations, well, since this is a tutorial on symbolic music, we will focus on symbolic alignment and just symbolic representations. But first, I want to point out the differences between audio-based alignment and symbolic-based alignment. In audio, we are basically aligning a time point or a timestamp in audio recording to a timestamp in another recording. Whereas in symbolic-based alignment, we can have this same time-wise alignment. We are aligning a time point from whatever object we have to a time point in the musical score or the musical symbolic object. Or node-wise alignment. We are actually mapping individual nodes in one of the recordings to a note in the score, for example. And this is what we will do in this notebook. A little bit for Sorry? Oh, but I was asked not to do that yet. Oh. Should I? Can you still hear me on Zoom? Sorry? Okay. Okay, then I will continue. Okay, great. So some types of music alignment. Oh, I think I know what is the issue. Can you still hear me? I think I figured out the issue. Okay, great. So we can understand alignment across two main dimensions. The first one being the representation modality of the objects that we are aligning, and then the time in which the alignment is happening. And so we can have multiple types of domain to domain, like for example, audio to audio, or symbolic to audio, or symbolic to symbolic. We have also some other more flavorful varieties of alignment, like image to audio alignment, where we start with images of the scores and then we are mapping that to the audio recording. And we have things like lyrics to audio alignment, where we are aligning the position of the audio with the text of lyrics. And with regard to time, we have offline alignment, where we have already the recordings that we want to align. And this is happening not in real time, and online alignment, in which case, if we are in a live performance, we can track a performance in real time. And in the MIR literature, this is usually referred to as a score following problem. And this is useful in a wide variety of contexts, including automatic accompaniment systems. But well, for this tutorial, we are going to focus on offline alignment. Let's see if this already set up, and then we set up. Okay. So as we mentioned, so we need to represent alignments, and one of the ways that we do it is with special formats. In particular, Partitura handles two types. The first one being one of our own, the match file format, which has been around for a while. And we just released an updated version of it for the Music Encoding Conference. So this is an encoding, or it's a file that includes information both from the performance, so basically contains all of the information that would come in a MIDI file, and it also contains some of the information that would appear in a score. For example, this is how a match file would look like. So it's a text-based file where we can read some information like, well, the version of the match file format and information about the piece. but also information about the MIDI, since all of the time, the performed time is represented in MIDI units. We have some properties of the score, like time signature and key signature. And the main objects, which are aligning the notes in the score and the notes in the performance, are these match lines, which match what we have here as a note in the score, S note, which has information. So it has an ID, it has its pitch spelling, and it has its temporal position represented in symbolic duration, and also in beats as a floating point number. And we can also include some other information. And we have the notes, which is just the representation of the MIDI. So the MIDI pitch, the onset time and the offset time in MIDI ticks, the MIDI velocity, and channel and track. We have also a second type of alignment line, which is the score time to performance time. So if we can have someone just tap along the beats of our recording, and then we can store this information, for example. And so since we can represent it as a list, if we have multiple people recording the alignment, we can save all of the alignments by the multiple people in the same file. If there are notes for note level alignments, notes in the score and the performance that do not correspond to any note in the score, we have these insertion lines. And if we have notes in the score that do not have an equivalent in the performance, we have deletion lines. We have some other information like different sections in the piece and the repetition structure, and other messages like sustain and soft pedal and whatnot. So if you want to see the full documentation of the match file, can be found here, and then you can look at the specification of the different lines. And so the type of information that it requires. But Partitura can read and parse match files. So for loading alignments, if you happen to have a dataset that contains alignments, so Partitura has a dedicated method to loading these, and we support two formats, as I mentioned before. Our match file format, which so there are at least a couple datasets with this, the Vienna 4x22, and an extended version of the ASAP dataset, which is currently under review. But I think the data is already available. And we have a third dataset that we'll release hopefully soon. And we also can support the format introduced by Nakamura and colleagues in 2017, which is one of the most used, if not the most used, symbolic alignment tool. And so for this method, we have two use cases. Either we have both a score file, a MusicXML, MEI, or something like that, or any of the other files that Partitura supports, or if we only have a match file of our own match file format. So if we only have a match file, we can just simply use the option create score, and the parser will import the performance information, the alignment, and the score. However, for a lot of applications, if we have the scores, this is kind of what we would prefer. The scores are more complete. And so you can just load the score and omit the create score flag, and then we will have all of the information that we require to do anything that requires performances and scores and alignments. What the alignment looks like actually is a list of dictionaries, each of which represents the content of a note. And we have labels where a match is a match, so that there's a corresponding note in the score and a note in the performance. We mark insertions and deletions. So if something is missing in the performance or something is missing in the score. And for some of the files, we also have ornament labels. So where we can specify whether a note is part of a trill. And for these lines, we specify, so for which of these performed notes in the trill is the corresponding anchor note in the score. So all of the notes have a score ID if there's a note in the score, or a performance ID if, so which one is the corresponding note in the performance. And this is why when we create objects like the note arrays, we are always giving an ID to the notes. But well, so we would like to get information from the alignments, and sometimes if we have a performance and a score, we would like to get the subset of notes of the performance and of the score that have matches, and we have a useful method, get match notes in Partitura utils music. And this will get us the indices of the match notes in the corresponding note arrays for the score and the performance. And then we can just get note arrays which will have the same length, and each of the rows would correspond to one note. And so yeah, a row in the note array for the score would correspond to the same row in the note array of the performance. Okay, so we move to the second part. If you remember this, this framework, we move to feature representations. And well, so ultimately we want to make the data comparable to algorithms, and we need to extract relevant features that capture the information and suppress all irrelevant details. And for our mathematical parentheses, we are going to represent this as sequences of features, basically 1D vectors, so that represent information from the score or the performance. And we are going to focus in this tutorial in two common feature representations, piano rolls and pitch class distributions. As Silvan mentioned in the previous part, piano roll is basically like a symbolic spectrogram. It's an image that represents on one dimension the pitch information, so the height of the note, and on the other dimension the temporal information. So let's create a piano roll. Let's create a piano roll and then come back to this. So here we have the piano roll of a score and the piano roll of a performance of the same score. We can see here, for example, that the piano roll of the score is strictly binary, whereas the piano roll of the performance, so the intensity of the note corresponds to the MIDI velocity of the performance. We have a few parameters that you can experiment with. You can specify the unit for the score and for the performance, so we can use either beats or quarters or whatever arbitrary division we have in the score to represent duration information entirely as integers. And this parameter time diff allows us to control the resolution of the piano roll. This would be how many units, how many cells in the piano roll correspond to one of the units specified here. For scores, if we use the automatic one, we will get beats. We have an option to add a separation of the notes. If we have, for example, repetitions of the same note in the resulting matrix, we would have just one single long note. But if we include note separations, the last cell, so the last pixel of the note will be left empty. We can remove the silence at the beginning of the piano roll, if there's any, and we can restrict so the piano roll to lie within the range of the piano, since a lot of things are recorded on pianos. And we have basically the same parameters that we can use for performances. And so as Silvan mentioned, the piano rolls are saved as sparse matrices, since most of the elements are 0. And if you want more information, so you can look at the compute piano roll documentation. So where there's a description of what every parameter does. Okay, the second representation that we are going to use today are pitch class distributions, which is kind of a symbolic equivalent of chroma features in audio. This is basically a piano roll that has been folded into a single octave. Then all of the instances of C has been folded to just one single C. And all of the instances of C sharp have been folded to one instance of C sharp and whatnot. And let's compare how a piano roll and a pitch class distribution look like. So this would be the piano roll of the score, and this would be the pitch class distribution of the same score. Right, so in here we have 128 possible MIDI pitch values, and here we would have only 12. So 0 corresponding to C, 1 to C sharp, and so on until 11 corresponding to B. Do you have questions at this point? Okay, if not, we move to alignment methods themselves. For aligning performances and scores, there are a number of methods that are traditionally used. The most common probably being dynamic time warping and hidden Markov models. And for this tutorial, we have chosen dynamic time warping, which is kind of a non-standard solution for symbolic alignment. Symbolic alignment has been traditionally dominated by hidden Markov models, but we are being rebels here. And so dynamic time warping is a dynamic programming algorithm, so where we can find the optimal alignment between two sequences. And this algorithm works in 3 steps. First, we represent the distance between the different elements in the sequence. And then we compute the accumulated cost matrix, which basically tells us how would be the cost of aligning different subsequences within the entire 2 sequences. And after we compute this matrix, we find the best alignment by backtracking over this matrix. And we have a simple example here. Which hopefully will be fast enough. Okay, we have here, let me make it a little bit smaller. Yeah, so we have 2 sequences, 2 very small sequences, and so 3, 9, and 8, and the sequence Y 3, 1, 9, 9, 7, 8. I think that for everybody is clear that 3 would be aligned to 3. So 3 would be aligned to 1, 9 would be aligned to 1, not to 9, and 9 would be aligned to 9, and 8 would be aligned to 7 and 8, right? So then we start by computing the cost matrix. So basically we compute the distance from one point to the other. Which we can do here. And then we use this to compute the accumulated cost matrix. Let me make it a little bit smaller. Yeah. So first we initialize the matrix according to the recursion. And then we use the iteration. So we are using the elements of the cost matrix, and then we are looking at the neighbor values, and we are getting the distance that corresponds to the minimum value. So, for example, in here, all of the candidates would be 6, 0, and 2. Or here, the candidates would be 2, 8, and 8, and so on. Well, I think the internet is kind of a little bit slow, and this is not being as responsive as it was before. But well, you get the picture here. And then finally, we get the warping path by backtracking, now that we have this matrix. So we start at the end, and then we consider which candidates and take the one that corresponds to the minimum accumulated distance. So, and then we finally have our path, right? So then one would be aligned to 3, one would be aligned to, so 3 would be aligned to 3 here. This one would be, so 3 aligned to 1. The second one, so 9 would be aligned to 9, 9 aligned to 9, 8 aligned to 7, and 8 aligned to 8. Right. So if you want to explore dynamic time warping in more detail, we have a small tutorial which you can look at your own leisure. But for the sake of time and keeping everything nice for the tutorial, so you can just do it on your own. For now, we have explored time-wise alignment, right? So if we have dynamic time warping, we would be aligning time points and not node level alignments. And for creating the node level alignments, what we can do is, once that we have this time level alignment, do a simple greedy search using windows following the time level alignment and just matching the nodes within these windows in the performance and in the score by MIDI pitch. So if you remember, we can create the piano rolls. If we use the option return indices, we get the indices of the notes in the piano roll. So which would be the pitch index. So wherever it's being represented, since in this one we are using piano roll range, this is not identical to MIDI pitch. And so where the note starts and when the note ends. And so let's compute an alignment using dynamic time warping and the piano roll features. And then we can use this greedy note level alignment to generate proper note level alignments, right? So then we end up with objects that look like the alignment shown before. So match notes that we have a note ID in the score and the note ID in the performance. And this is all fine and nice, but we want to compare alignments and we want to evaluate how well different alignment methods work. And we would like to also to be able to correct alignments, since this is useful for other tasks. So for this, we have a few things. Let's first start by getting some alignments with different methods. So we are going to compare the pitch class piano rolls versus regular piano rolls. And then we are going to test a very simple linear alignment. So instead of using dynamic time warping, we use a linear alignment where we match the first score, the first note in the score to the first note in the performance, and the last note in the score to the last note in the performance, and then we just create a line in between. So let's visualize these types of alignment. So this is how it would look like, and if we zoom in, we see that so there are some differences. And if we want to inspect the differences between these alignments, we have a tool that was developed by Silvan called Parangonada, which we can have a look at. So in this tool, we can compare alignments So it's for correcting alignments, but also for comparing different alignments. For example, let's generate here. So this generated some paragonal files as a zip file, which we can download. And we can load them in Parangonada. And we can visualize the alignment. Okay, here, so we can see a few things. So in this tool, we can zoom in and zoom out of the performance, and we can move in the performance, or we can move only in the score. Each of these boxes in these piano rolls represent notes. And so here is the pitch spelling of the note. And the lines represent alignments. Since we have two types of alignments, in here we exported for comparison the alignment from dynamic time warping using piano rolls, and as a second alignment, the one generated from the dummy linear alignment. So in here you can read the instructions, but so we can just represent the alignment. This would be the alignment from dynamic time warping, and this would be the alignment from the dummy linear alignment. The notes highlighted would be the ones where the alignment differs in the two versions. So here, if we look at these two alignments, we can see which notes are being aligned differently by each of the algorithms. And so here we see some errors. And we can use this tool to correct alignments as well. Furthermore, so we could use this tool to generate alignments by beat, by tapping the beat. So you can just start tapping the beat, and then this would record some where the position of the beats would be, and then we can use this to generate more precise note level alignments. Mm-hmm. Do you have questions at this point?
Yes, sir. Can I start?
Okay, so moving on. So we have presented a tool for comparing alignments and correcting alignments, which is sometimes useful.
Can I ask a question?
But well, so we want to compare alignments quantitatively, and we can evaluate note level alignments by comparing how precise they are by computing the F-score measure of so whether the notes are correctly aligned or not. And if we do this, we can see that the linear alignment has a very low F-score. Whereas the alignments from dynamic time warping and piano roll have a relatively high F-score, and the ones from pitch classes have better than the linear alignment, but worse than the ones using piano rolls. You could try, for example, to change the parameters of the piano roll, changing the resolutions, for example. Something that is quite useful in these cases is try to match the resolution of the performance piano roll so that is kind of similar size to the piano roll of the score. And well, so the final part of this section of the tutorial would be some applications of alignment. And for this case, we are going to focus on comparing tempo curves. Since we have multiple performances, then we have, so we can extract the tempo curve of the different performances. And for this, we are going to get all of the performances of one of the pieces in the Vienna 4x22 dataset. So this is the first part of the Etude Opus 10 number 3. We have utility called get time maps from alignment, which then will compute maps that would map score time to perform time in the score and the performance given the alignment. And we can use this to compute tempo curves, but by just comparing so the time that a beat takes in the performance and what a beat takes in the score. And we can compare with these nice plots. So in this plot, each of the lines corresponds to one of the performance by the 22 different pianists. And the black line is the average of them. We can see, for example, that there are a lot of commonalities across the performances, but there are some clear differences showing that how each performer has a different interpretation of the piece. And we can use this kind of analysis for a variety of other tasks. So yeah, this is the ending of the music alignment part. Do you have any questions?
Yes, sir. Can you, am I audible? Am I audible, sir? This is Kumar here. Am I audible?
Thank you. How do you handle repeats? How do you handle repeats?
Well, repeats are hard. So at least dynamic time warping is not very good at handling repeats. Okay. So dynamic time warping is basically assuming that you have both performances and scores that have the same unfolding. This is, well, not particularly good for dynamic time warping. There are other algorithms that are better. There's a variety of the Needleman-Wunsch algorithm that an extension with dynamic time warping proposed by Martin Krachten and Martin Gasser in ISMIR 2013 that is slightly better at handling skips. And otherwise, you are in the territory of hidden Markov models. Hidden Markov models are better at handling this thing within certain constraints.
Okay, and for ground truth match files, for example, we have a match between a note of the score and two notes.
Yes, so what match files would do when they unfold the score, the match files codify, so there's a -1 if there's so the first repetition, -2 if it's in the second repetition, and so on. And we have a method where you can get the optimal unfolding of the score given an alignment. But yeah.
To just add to this, since it's also about Partitura, Partitura does handle repeats. So if they're marked in the score, they're loaded into repeats, and Partitura has functionality to unfold repeats as marked in the score, including jump markings like dal segno and al coda and stuff like this. And what Carlos just mentioned, this unfold parts to alignment, basically uses this functionality and an existing ground truth alignment to figure out what repeats should be played ideally to best match a given ground truth alignment.
Other questions? Questions in Pigeonhole? Okay,
Hello,
so then I think we can move to the final part of
can I ask
the
a question,
tutorial,
sir?
which Manos will present.
Can I ask a question, sir? Hello?
Okay, so we will be back in 5 minutes while we change computers. Oh, yeah, there's a hand.
Yeah.
Yeah,
am I audible,
go
sir?
ahead and ask your question, I think.
Am I audible, sir?
You can
This is
unmute yourself, I think.
Can you hear me, sir? Hello?
Hey.
Can you hear me, sir?
Yes.
Yeah, thank you so much. So I want to know actually if I want to do the comparative analysis. Now take for example, two person is playing a piano. One is the master coach and other one is a beginner. So definitely the alignment will be not be accurate. Can we use this alignment techniques over that to have a comparative analysis between the two persons singing means playing a piano songs?
I mean, so if you have an alignment, so then you can compare the differences between what would an expert performer would do and what a beginner would do. And you can use a number of different techniques to compare the parameters like the tempo curves or the dynamics or the articulation. And then you can create some sort of models that could identify which types of variations are more common in expert performers and which ones would be more common for beginners.
Okay.
Miriam, I hope that answers your question.
Yeah.
Okay. Okay, well, so we will take a couple of minutes while we switch computers.
Okay. So if everybody in Zoom can also hear me, let's move on with the last part of this tutorial, which also will be breaked in two different applications. So to follow along, even through the website locally or through the Colab, you just go to the pitch spelling with Partitura, which is going to be the first part, the first task that we're going to see, and open it in Colab. Or you can just follow along in the website. All right. So now we're going to see how we can deal with some machine learning workflow and how we can deal with some of the popular or less popular tasks, symbolic music tasks. So the first task we're going to talk about it's about pitch spelling. And pitch spelling, okay, maybe can I do this full screen? Nope. Okay. All right, let's leave it as it is. No. Okay, pitch spelling is about assigning pitch names onto MIDI pitch. So it's all about relating MIDI pitch or frequency to note names plus accidentals, such as sharps, flats, double sharps, double flats, or natural signs. So the task of relating a frequency and to its spelling, to a pitch spelling, is not trivial. It may depend on many things, such as the tuning when we're dealing with frequencies, the temperament, and all this. But when we're dealing with MIDI pitch, this is just about relating the MIDI pitch, which is a value between 0 and 127, to a related tuple with a note name. And this naming convention is usually in letters such as A for La, B for C, and so on, and accidentals. So let's jump directly into some concrete examples so we can visualize what is pitch spelling about. So in this example, we have two different spellings, actually two scenarios, this one and this one, up and down with two different spellings. So in the first example, we have an A sharp that can also be written in B flat. And this is a different spelling for exactly the same notes. And in the second example, we have a C flat that can also be written as C sharp, as B sharp, which also relates to different spelling, but the same content. How to correctly spell a note may depend also on harmonic progression or the context around music. For example, a very popular concrete example would be the augmented six, where for example here we're in A minor, and we have an augmented six going up to a dominant chord. Or we can have the exact same content, but in this case it's just a borrowed dominant chord that goes to another tonality, B flat major for this example. And if we're dealing with this progression, we may want to spell our music differently depending on the context. Augmented six, usually we have this D sharp, which will go to E, or in this example it goes down to the seventh, the natural. Where we've had dominant, we just want to spell it differently because our content is related to the harmony. So please don't worry if music theory is not your thing and this does not tell much to you. We're gonna see a computational approach to solve this task. So this is not very important to follow along. Let's start with some popular pitch spelling algorithms. As said before by my colleagues, and Carlos in particular said that the built-in music analysis features that we have in Partitura. There is a feature about pitch spelling in Partitura called PS13, pitch spelling algorithm by Meredith, published in 2006. And some other notable algorithms, and the one related to this tutorial is the PK spell by my colleague Francesco Foscarin, presenting in ISMIR of 2021. We're going to see how to build a similar model to the state-of-the-art, the PK spell, and how we can use it together with Partitura to build a pipeline for training a model and doing some pitch spelling. So in this tutorial, we will use some packages, first and foremost Partitura, but also some machine learning packages such as PyTorch or PyTorch Lightning, which it's for those who don't know, is just a wrapper for PyTorch, so we can get encapsulation of our models and better visualization, and Pandas for mainly for visualization of the alignment files and the pitch spellings. So let's start by downloading the ASAP dataset containing note alignments of symbolic performances and their respective scores, which will be a perfect dataset for pitch spelling. Oh yeah, please trust us. So as I said before, the ASAP dataset is a very big dataset that contains scores and note aligned performances. So this would be a perfect scenario for pitch spelling, where we want to basically take the performances for which we have MIDI pitch and associate them to a pitch spelling which can compare directly with a score. So let's say some more about the ASAP dataset. It's a big dataset containing both MIDI and MusicXML for the scores, and for performances also contains audio and MIDI with all downbeat, beat, note, time signature, and key signature annotations. For this tutorial, we're going to focus on the note annotations between the MIDI performances and the scores. To date, ASAP is the largest available fully note-aligned dataset. It contains 236 musical scores and 1,067 performances of Western classical piano music. And this is a more analytical table of every composer and the related number of score and performances. So for accessing this information, maybe this dataset will be a bit too large to train a model on our local computers, or even for Colab, it will take so much time. So we will focus only on the Bach performances for this tutorial. But feel free after to just change the settings and train an even better model and see how far you can get with this pitch spelling. So let's start by here accessing the directories of the ASAP files. And you can see here that I'm accessing only the Bach files. We're going to need also to split those Bach files into a training set and a test set so we can test our pitch spelling model. And for this, very randomly, we just picked as a testing scenario the Italian concerto of Bach, where for training, we just use preludes and fugues. And as we saw previously, the MATS format will be a very convenient format for this tutorial, so we can relate, so we can access directly the pitch spelling and the relation between the performance MIDI and the actual score. So let's go ahead and produce the matches from the alignment files. So this might take a while. So maybe while this compiles, we can see a bit more information about where the dataset is stored and how the alignment information looks like. So we're just taking the Bach files here, and we're using the Italian concerto files and the relevant performances for testing, while we use the fugues and the preludes for training. And maybe if there is already compiled, we can already see the note alignment, and we're gonna produce the MATS files for this. To produce the MATS files, we just select from the list of alignments the XML ID to the MIDI ID, and then we relate them. And of course, we put three different tags: deletion for notes that exist in the performance but do not exist in the score, insertion for notes that exist. Sorry. So deletion is for notes that do not exist in the performance but they exist in the score. Insertion is about notes that exist in the performance but they don't exist in the score. And MATS is about a performance note that is matched with a score note. So maybe we can go on and talk about the pitch spelling model and what we need to initialize this model. So as we said before, the pitch spelling is about relating MIDI pitch to a tuple containing the note name and the accidental. But maybe we can simplify the scenario, because we can, instead of the MIDI pitch that also contains implicit octave information about the pitch, we can directly associate the pitch class. And the pitch class is the separation of a tempered octave into 12 semitones. So we use 0 for a C note or a Do, and 1 for a C sharp or D flat. And you can see on this up to 11 for a B natural. So you can see on the right column, we also have all the possible spellings that we can have for every one of those pitch classes. And for example, let's read the first one. For 0, we can have a C natural, a B sharp, or a D double flat. And it may look weird to you that the A flat or G sharp only has 2, is because we covered all the possible combinations of spellings up to 2 flats or 2 sharps. All right, still compiling here. This is taking a bit longer. So maybe I will continue with the explanation. Given this table, we may characterize a note by the triplet, associating a note to a name, an accidental, and an octave. And this would fully encode the pitch spelling of a note that we saw also earlier. This is the way that Partitura internally encodes it. A name associates to one of the A, B, C, D pitch names. The accidental will output 0 for a natural, +1 for a sharp, or +2 for a double sharp, and -1 for a flat, -2 for a double flat. Octave, of course, relates to the octave. For example, an A4 that would be usually 440 hertz, would have a name of an A, an accidental of 0 for natural, and the octave 4. So it will attribute to the triplet A04. All right. So our matches are now produced, so we can go on and, of course, divide our match files into train and test, and initialize exactly as is explained here, our pitches, associating the pitch classes to their associated spellings. So to create pitch spelling dataset from the ASAP, we will use the match files, as we said, that associate the MIDI performances that are not aligned to score, and we produced that earlier. But for this task, we only need to, we can only evaluate to notes that actually have a match between the perform notes and the score notes. So therefore, we're gonna look for the tag match and only evaluate on these notes. So the training procedure will only happen on match notes. Then we will obtain pairs of notes of performance note and score note, and this is what we will use. We will use the performance note for spelling and the score notes for evaluation. All right, this is everything that we said. So something more is that our performance notes have some attributes such as the MIDI pitch and the duration that we're going to use for training our model, where the score notes will have this triple that we said earlier about note name, accidental, and octave. So let's talk about feature extraction, what we can use as features in this setting. So we chose to extract from the MIDI file a 14-length vector that will contain the first 12. For the first 12 values, we use a one-hot representation of the pitch class, extracted from the MIDI pitch by just doing a modulo 12 operation and building a one-hot vector of this. A normalization of the MIDI pitch between 0 to 1. That will also attribute to some kind of octave information, and a duration normalized by minute. The tokenization of the score notes follows the previous table of the available spellings that we saw here, and we just associate just a value to every one of those possible spellings. So if we look at it as a classification scenario, we just have 35 classes, and now we're ready to create our features or labels. So now, while we create our data from the match files, we create our features and our labels as said so earlier. So now we can talk about our pitch spelling model. As I said earlier, we're going to use a variant of the PK spoil model that was developed by Francesco, Foscarin, and colleagues. It is a sequential model, essentially an LSTM block followed by a linear projection layer. So the performance nodes are actually sequential, since MIDI messages are passed in order, while the score is more like a hierarchical representation. So yeah, please note that actually the original version of the PK spell model was not trained onto performances, but since the capacities of Partitura now make it easy to create this workflow very fluently and run it with a few steps. So now we can train on the performances and use ASAP to evaluate on the scores. So as I said earlier, the model is just comprised of an LSTM model and a linear projection. And of course, since this is a classification scenario, we use this cross entropy loss. We will also need to introduce some PyTorch and PyTorch Lightning wrappers for the dataset and the model. So let's go ahead and run the next cell. So now we arrived at the crucial point that we defined everything. We're ready to train our model. For training, we'll use this PyTorch Lightning trainer object, which is basically a wrapper that takes our PyTorch model that we defined earlier along these data sets and the other wrappers that we use for. And this will just show everything a bit more easily with a progress bar so we can follow along. So for this tutorial, I would only train our model for maybe less because it will take some time, only for 3 epochs. But of course, if you want also better results, you should train maybe a bit more. So let's go again over the model and explain a bit more. As you see here, the input dimension of our model is 14. This is about the one-hot vector representation of the bits classes. When the MIDI bits is given, we just produce the bits classes and transform it to a one-hot representation, plus a normalization of between 0 and 1 of the MIDI bits and a duration normalized per minute. So we embed using a LSTM layer into a hidden dimension of 100, and we also project into a linear projection layer to the number of out bits, which equal to 35 different possible bit spellings. So maybe while our model trains, if there are any questions and anybody would like to ask about the workflow until this point. All right. So again, what are we doing? We're using the Bach fugues and preludes for training, and we're evaluating on the and we will test also on the Italian on the Bach Italian concerto, taking MIDI bits and giving 35 different spellings per MIDI bits, associating every note of the performance to a triplet, well, the bit spelling that we have the ground truth in the score. Maybe I can show again until this trains 35 classes. Okay, I think we're ready to go. Once our model has trained, we're ready to use it for prediction. And we can maybe, okay, we're almost there. Oh yeah, maybe I can direct you to the original PSK-Spell repo, which you can use for a bit more advanced. Well, this model was originally taking the ASAP scores for training, but it also was doing a key estimation at the same time. So if you want a bit more context and a bit more advanced models, you can just check this repo here. All right, so now our model has trained for 3 epochs, and we can use it for prediction. So let's select the MIDI file, load it using Partitura to a performance, and use the model to predict, to use a variant of the PK spell model to predict a spelling. And we can print the first lines, the first predictions. And you can see here we project everything into the triplet containing the step, where the step is the name, the alter, which alter is equal to the accidentals. 0 stands for natural, and the octave. In Partitura is also very easy to obtain directly the bit spelling from a performance using the PS13 algorithm, and this is very easy. We just load we just input a performance into the MusicAnalysis.estimate spelling, and we can directly visualize. You already see that the first lines look very, very similar of our trained model and the bit spelling estimation. So maybe at this point, I can just explain a bit more how the PS13 works. It basically does local estimation of key and uses key profiles to estimate the spelling for per bar. So we can use the same pipeline to compare the spelling of our trained PK spell model to the built-in Partitura spelling estimation plus the ground truth. So we can compare the PK spell variant trained only on back, the built-in tool in Partitura, and the ground truth. So let's do exactly that. We load the score and the MATS file. We get the performance and an alignment for the MATS file. And of course, the baseline spelling using the built-in Partitura PS13 algorithm, and our prediction spelling using the variant of PK spell model. We also obtain the ground truth from the score in the next cell. And here we can output the prediction between the Partitura and the PK spell. And of course, here you see that the PS13 at this point performs better than, well, the state-of-the-art trained only on back. Well, a variant of the state-of-the-art. And this is completely normal because we didn't use so much data to train this. But if you want to go ahead and load more data and train a much more powerful spelling model, you can of course try this, and you will gain even more spelling power and be able to spell all kinds of scores. So this concludes the PIT spelling tutorial. But let's see how we can maybe use Partitura for. Actually, I can take a pause here to answer any questions regarding PIT spelling, if there are any. Are there any in the chat, in the Zoom? Okay, so maybe we can directly move along to the. So the very last part of this tutorial is about drum generation using a transformer. And you can, of course, follow along as with every other using your local version of the repo, the collab, or the website. So let's open the collab. So in this tutorial, we will learn how we can train a small autoregressive transformer model together with, well, for simplified drum beat generation in MIDI, of course, in symbolic format, using Partitura as our main tool that we can import those MIDIs. So at the end of this tutorial, we'll be able to create a simple drum beat of a bar's length. And we also see some useful techniques about encoding MIDI and how we can input this into a transformer, how we can do some tokenization and some representation about symbolic formats. So let's, of course, we always start by installing Partitura, the most important step. So in this tutorial, we also have some other dependencies, such as not too dissimilar to what we saw before, such as pandas. We also use torch and of course Partitura. We also use torch for the model and the training process. So we also need some external files. And if you clone the tutorial locally, then you already have this. We just assume that you're running the notebook from the parent directory of the tutorial. Otherwise, go ahead and just run the cell in the collab, it would work. All right, let's talk about the dataset. In this tutorial, we will work with the group MIDI dataset, which contains MIDI drum grooves from a multitude of genres. So for simplicity in this tutorial, we'll just only use the MIDI files that have a 4/4 time signature. For loading, we will use Partitura. And if you want to load a preprocessed dataset, or if you already run the tutorial, run the collab or the notebook, and you don't want to redo all the dataset process, you can just save the 2 cells to saving a preprocessed dataset so you can edit stuff around without redoing the whole loading process. So let's first take a closer look into the data and plot the histogram of tempi from all the target pieces. These are all the pieces with the tag signature 4/4. So we can see here that we almost have something like a Gaussian distribution where it picks like a mean around 100 beats. Well, it's not true because you also have a gap and not very equal. But we can see that most of the drum beats we're going to see here are around 100 beats per minute, and there are also some around 120 or 125. So let's go ahead and load the data, and I'm running the cell directly because it might take a moment. So what we're doing right now is we're taking the data and we're loading it into sequences of a measure length. Since for our training process, we only input a measure length drum beat, and we're trying to predict autoregressively a bar also for a measure length bar. So we can also view the histogram of the durations of all pieces. And you can see here that most of the pieces are relatively short. So that would, like the majority of pieces would attribute to a length of 10 bars or so. It's not very visible, but there are a few longer pieces, but the majority of pieces are relatively short. So let's go to the important part, which is about segmentation and tokenization. So we need to find a way to reduce the encoding of the MIDI and the sound profiles. So we think about, well, we saw here an approach of how to take MIDI information and compress it for this minimally trained transformer model. Our first task is reducing the encoding of the MIDI sound profiles. It means which MIDI bits will attribute to a sound profile for our drum sampler when we'll use the MIDI values. So there are 22 standard percussion MIDI sound profiles, and we project them right here together with their MIDI pitch. The standard associated sound that will go to these MIDI bits. For example, the MIDI bits 36 is attributed to a kick, and the rewritten sounds where we just compress this information to only use 6 sounds as target. So we attribute the MIDI bits 36 to a kick, and the kick will be written by kick. But we can see here that the 37, 38, and 40 are some kind of different snares, such as the X-stick snare sound, or the main snare sound, or the rim snare sound, and we attribute all this to a single snare sound. In summary, we can say that we're associating the MIDI drum sounds to their sound category or family. So snare type sounds will be attributed to a single snare sound. Tom like sounds will be attributed to the single tom sound. So we can also use techniques to reduce the MIDI velocity encoding. And this is what we use is this formula right here, to just obtain 8 classes of velocity. So we only have not 127, we just reduce this to 8 main classes of different velocities. We can do, similarly, we can do the same about tempo, for which we use 8 classes as well of different tempi. We also use beat or fill characterization, where we saw for every bar in our data set, if it has like more like a soloist character or more like a main drum beat character. So in the second case, we attributed beat, or when it's more like a solo or a fill part, we attribute the characterization fill. And we can also likewise reduce the time encoding. But for this time encoding, we used a more a hierarchical division in base 2 representation, where we start by separating the bar in 2. one for like the first part for the first half note and the second part for the second half note. You remember we only have bars of time signature 4/4, and we continue this process for quarter notes, for 8 notes, and so on up to 128 notes. So we use a binary setting in hierarchical level to encode all the different quantized information within a measure. So we will get a binary hierarchical representation, and let's see an example here for the second 16th note of a bar would be this vector here, which will have 0 for the first half note of the bar, 0 for the first quarter note of the bar, 0 for the 8th note of the bar, and 1 for the second note of the second 16 notes, and 0 everywhere else. That would mean that would be the 16th note of the second 16 onset of the bar. And using this representation, we can only use binary for all these different hierarchical values. So let's do exactly that and initialize the pitch encoder, time encoder, velocity encoder, tempo encoder, the measure segmentation, and of course the pitch mapping. And we can visualize directly the first tokenized note of the first sequence, would be something like this. The first values is the timing encoding, the hierarchical timing encoding that we saw here. So since it's the first node, I assume it will be a kick, probably. So it falls in the very first onset, and it has a velocity. This is the sound. And the last one is the beat characterization, and this 2 is the tempo, if I remember correctly. So let's go ahead and try and generate our segmented trained data and a reduced encoding for our trained data. And we can also show the train loader shape, which means we basically have a batch size of 127. And in our batch size, we have max sequence length of 35 nodes. And the number of tokens is, of course, 11, as we saw earlier. So these next 2 parts is if you already run the notebook and you want to change the settings of your model or anything else of your tokenizer, but you don't want to reload all the data, so you can go ahead and uncomment these 2 next cells to save pre-processed version of the data set. So let's talk about the model. As we said before about the time encoding, the tempo encoding, the instrument encoding, and the velocity and the beat. We just use binary information for all the timing encoding, starting from a half note to an 8 note to a half note, a quarter note, 8 note, 16 note, and so on up to 128. The instrument decoding, the velocity, the tempo that only has 8 classes, and the beat that only is also again binary. So we choose, we embed these one-hot vectors to actual a 4-dimensional vector, which we will see why just on the output. We concatenate all these representations and we use it as an input to our transformer model. It goes through a positional encoding cell up to a typical transformer cell already implemented in PyTorch, and followed by a linear projection layer. So the output of the model is again a concatenated representation, which we cut into the appropriate segments similar to the input segments. So we can, and we use the sigmoid activation to get the most probable value for gaining the offset, the onset instrument, etc. So the reason that we use 4 vector instead of 2 for binary representation is that we reserve for every one of those separate representation, we reserve 2 more values for the start and the end token. So in summary, the binary one-hot vectors go from two-dimensional vectors to four-dimensional vectors, where the third position is for the start token, the fourth position is for the end token in the output representation. And for consistency, we also repeated the same dimensions in the embeddings of the model. So let's go and run this cell about initializing the embedding with the dimensions that we talked earlier, and initialize also the training loop and the fit function. Oh, all right. We can now initialize our model. Oh, sorry. So of course, we need to initialize depending on the figure that we saw here. So let's go ahead and initialize the token dimensions as we said earlier. And we can see the number of parameters on our model. So it's a relatively small transformer model with 264,000 parameters, more or less. And you can also call the loop only to train or retrain or fine-grain your model, but we will skip this on this collab. So we load a pre-trained model that has been roughly trained about for 200 epochs that you can use to directly generate. And let's maybe fine-train for 3 more epochs. So as the model trains, would there be any questions on the process and the workflow for training this model and what the encoding we did was for? Maybe in the chat. Okay. So to reiterate once more, we took the MIDI files that have drum beats. We segmented it into bars. Every bar, we only selected the files that had time signatures of 4/4. And we tokenized this MIDI input representation into very particular time encoding, tempo encoding using 8 classes, instrument encoding using 6 classes, also velocity encoding for the dynamics using 8 classes, and a characterization if it's a beat or a feel for this drum bar. Of course, by no means this representation that we use is a standardized one. It's just the one that we preferred for this tutorial. You can, of course, go ahead and change it however you will, and maybe inspired by this or use another thing that you like to represent your drum beats like. You can, of course, also use even more data if you want them a different kind of prediction or different kind of sampling. We can also see that for the pre-trained model, the loss is not really decreasing. All right. Just a few seconds more. Maybe let's talk about the sampling process while our model finishes training. So as we said, this model is autoregressive, so it will start by predicting, well, we'll start from a start token, and then we'll start predicting the next note in the sequence until it finds the end token, and then the sequence ends, and we have a bar length of music. So this happens autoregressively, 1 note at a time, and this is how we will call our sample loop. There is an initialization with a start token inside our sample loop, and then a prediction of a certain number of notes. I think in our case, it's just 31 notes. And we obtain a prediction. Maybe we can directly view this prediction, and I have right here. And as we can see, I projected into this table that has the different encodings that we use, the half note, the quarter note, and we can see the first note here has zeros everywhere, starting in the very first note, using a Pitts instrument 3. And velocity 0 and tempo 0 and tempo 2 a bit type 0. And we predict 30 notes, but as you can see, only 11 of those notes are actually included in the bar, and from the 12th note onwards, we only get the ending token. So our model decided that 11 notes are enough, and we don't actually use the whole 31 to fill the bar, and then it just predicts the end token until the end. So finally, if you're going to use this, you can very easily generate and save those MIDI files, and you can find them in your collab right here, and you just can download them, put them in your DAW preference, load a drum VSTI or create your own drum sampler, and play along with these files. So in summary, in this tutorial, we learned how to create a very simple MIDI drum generation using Partitura and Transformer autoregressive model. We're investigating some possibilities for the timing encoding and for the pitch encoding, and how we can reduce the information that we get from our original MIDI files, for example. And this is the end of the whole tutorial sessions and collabs, and interactive collabs. So I would like to take a couple more minutes to just introduce some more applications that use Partitura, such as the 2 publications that we saw in this conference. So you can come along, visit our poster, and ask more about Partitura or about this publication. The one is they're both in Symbolic music about concept-based techniques for musicology learning explanations in deep music learning classifiers. And the second one is about cadence detection in symbolic classical music using graph neural networks. So I will just leave this up if you want to scan the QR codes to get the PDF of the papers, or you may as well find us later in the poster sessions. I think both of them are presented in the 7th. So thank you all very much for joining our Partitura tutorial. We're kind of finished a bit early, I think. So we can maybe take this time for an open discussion or for questions about any of the parts that we saw earlier, about introductory in Partitura, alignment using Partitura, or 2 different applications on pitch spelling and drum generation. Oh. There is a question.
Hello. I was just wondering whether we have any kind of validation functions within Partitura, which can help us understand whether files are valid or not. For example, in this MIDI generation example, we could get sequences that are not valid MIDI. And in such a case, can we use Partitura to find this out?
So if the MIDI is not parsable via MIDO, then it would just throw an error.
Okay, but we can't get a true or false from Partitura. Okay. Yeah.
Well, you can get an error, so it's pretty close.
So at least for other score formats like MusicXML, so we can validate a file. There's a method for validating whether a file is correct or not.
And Partitura is also very generous about warnings, to the point that it's sometimes a bit annoying. So it will warn about all sorts of stuff that it cannot parse, at least in symbolic formats.
Yeah, maybe to elaborate a bit more on this, there is a multitude of warnings about slur endings not found, or bars that are more than the bar length that is allowed, or less than the bar length that's about. This is all about symbolic formats such as MusicXML, MEI, or Kern, and you can find a multitude of mistakes or, well, encoded in a very particular way scores that are not the very typesetting correct way, for which we account using warnings, notifying the user if a slur is going to be dropped, if it doesn't have an ending time point or whatnot.
So thank you for the presentation. Is there any additional feature or something that you are planning to integrate in Partitura, something that, what are the next steps?
Well, I think any of my colleagues will give a slightly different answer to this, but Partitura needs to be a format about importing and exporting symbolic music formats and making the life of the symbolic MIR engineer very easy, without diving very deep into musicological questions or musicological understanding about how everything works and how it's connected, giving a simple timeline, very clear instructions, very clear functions, how to extract information using the note array, the piano roll, and a list of features around that. What everything comes above this, such as tokenizers, trainers, we want to create a separate package that will work in unison with Partitura, but not necessarily to deal with all these extra steps.
Yeah. If I can add something on that. So everyone that has worked with symbolic music before knows how problematic and frustrating it is to work with these files, just because there are a lot of exceptions and you may want some people encode it in a different way and stuff like that. So of course we try to be as general as possible, but if you're working on a specific problem with some specific scores, yeah, there will be something that need to be integrated. So this is also part of the development, and it's also something that you can do. For example, on GitHub, you can open issues and you can collaborate with us. This is, unfortunately, I mean, it's impossible to cover all the edge cases that exist in SCORE. So what we do now, what we've done for the past years, is that we start doing some research like the one that you saw, and during that we found some exception in scores that then we include them in Partitura. So of course, if you start using these packages, it's possible that you will find some yourself. Then this is ongoing stuff. Then we will try to solve. If you have some ideas how to solve them, you can of course contribute, and that will be an ongoing stuff, probably forever, because there are too many things.
We are of course very grateful if you open an issue on GitHub of any requested features or any bugs that you find, because these things are, as Francesco said, like endless. There's an endless list of features that we can add on the scores, and everybody has a different set of interests about what they want to see in the score. So we were very grateful if we hear your voices and what you want from this package, which is after all oriented towards the whole community. And finally, also we will be happy if you can start us in GitHub. All right. If there are not any more questions, then thank you very much for joining. And